let's talk about complementary submodules. Complementary submodules. So this is related to the notion of direct sums that we talked about before. So let M be an R module. Let M1 be a submodule. Now if M2, so if there exists a submodule M2 of M such that M is the internal direct sum or the direct sum of M1 and M2, then we say that M1 has a complementary subspace. So we say M1 has a complementary subspace or a submodule, has a complementary submodule. Okay. And in this case the complementary submodule is M2. So we say M2 is a complement of M1, and we say further that M2 is a complementary submodule of M1. Okay. Now the point here is that you may not in general have complements. Given an M1, there may not exist an M2. That's something that happens. And the other important thing is, even if it does have a complement, the complement need not be unique. There are often many different submodules, each of which serves as a complement to the given module. Okay. So let's just look at some examples here. The most familiar one is that of subspaces or vector spaces. So this is the case when R is a field K, and so M1 and M, so let's say M is a K vector space. In other words, it's a module over the ring R equals K, and M1 is a subspace. Okay, so I am given all this. So the question now is, does M1 have a complement? Okay, is there a complementary submodule of M for M1? Does M1 have a complement? Okay, and the answer in this case of vector spaces, or in the case when R is a field, the answer is always yes. Okay, so M1 always has a complement. So claim is that I can manufacture a complement for M1. M1 has a complement. Okay. So this is complementary submodule really. So as a complementary submodule. Why? Well, here's how we usually do this in vector spaces. It's probably familiar to you. So let me just draw a sort of a schematic diagram. So let's say my vector space is, so as an example, suppose my field was the field of real numbers, and suppose my vector space was M equals R2. Okay, and suppose I gave you M1 to be, let's say, the x-axis. So let's say this space here is M1. Okay, and what I need to do is to find a complement to M1. Okay, now as you can see, there are in fact tons of different complements. Of course, I could take the y-axis as a, here's one possible complement, but in fact there are many others. I could take any line other than the x-axis. Each line other than the x-axis will serve as a complement. So these are all different choices of M2. I can take this to be M2, or I can take this to be M2, or I can take this to be M2, and so on. Okay, so I have many choices here. And what is it that we are really doing? Well, what we are doing in this picture can be done in general. So how do we find a complement? Well, here's the construction. Let's just do this via bases for this vector space. Okay, so how do we manufacture a complement? Choose a basis let's call it VIs. So at this point I am just allowing everything to be maybe even infinite dimensional, I don't care. So choose a basis Vi of M1, okay, and the key point here is that this basis can always be extended. So and extend this to a basis. Okay, let's call this. So I already have some basis vectors. To that I add a few more. Let's call it Vi primes, I belonging to some other indexing set J. Okay, so I can, given a basis for a subspace, or given in general a linearly independent set in a vector space, you know that you can extend it to a basis. You can add on some additional vectors so that the whole set is a basis of the ambient vector space. Okay. Now this is a very non-obvious and important property that vector spaces have, which general modules don't. Okay. So let's do this. You can extend this to a basis, and now what does that get you? Now what we can do is we can use this extended basis to define the complementary subspace. So I define M2 to just be the span. Okay. So this is span over K is span of the remaining basis vectors Vi primes I in J. Okay. Now once you do this, so like we did in this figure, observe that the ambient vector space is nothing but M1 direct sum M2. Okay. Why? Well, again I will leave this for you to check, but you can already see why this must be true, because if I give an arbitrary element M in M, I first write it as a linear combination of these basis elements. Some terms involve VIs, the other terms could involve the Vi primes. So the portion which is a linear combination of the VIs, I call it as M1. The portion which is a linear combination of the Vi primes, I call it M2. Okay, and now use this to show that this decomposition is unique and so on. Okay, so if you are in the context of vector spaces, then any submodule of my module M, or rather any subspace, therefore can you can always manufacture a complementary submodule for it. Okay, now this fails in general if we are talking about arbitrary rings. So this is not true in general, and let's see an example where this fails. Okay. So for this we will just take R to be the ring Kx, the ring of polynomials in one variable x, and if you remember what modules over this ring are given by, they are just pairs V comma T, where V is a vector space and T is a linear operator on V. Okay, this is really how any module over this ring can be obtained. So in our case, let me take V to be something very simple. Let me take V to be the vector space K2. Okay, so it's, I think of it as all column vectors, all 2 cross 2 column vectors, A and B coming from K. So this is my vector space, and I need to also specify a linear operator on this vector space, and I will just give you the matrix of this linear operator. So this is 0 1 0 0. So recall we have looked at this example once before when we talked about quotient modules and so on. So T is just this operator. Now what does this mean? Again, to recall how pairs V comma T correspond to modules over Kx, the translation is the following. When I take a scalar from my field, so if I take alpha scalar from my field and I make it act upon an element of V, it just acts as usual. It just multiplies. This is the definition of scalar multiplication in K2, right? I just multiply alpha on both components. So this for all alpha coming from K. Okay, so I think of alpha as the constant polynomials, which is they only have a constant term, no x or x square and so on. Next I tell you what x does. How does x act? Well, x acting on an element of this vector space is given by the action of T on that element. Okay, so T really performs the role of x, and in this special case, what is T on AB? I just need to multiply this 0 1 0 0 on AB. So that's just B comma 0. So this is how x acts. X acting on AB gives me b comma 0, and in this particular case it's easy to check if I take x square, for example. So x square is supposed to be t square, right? I perform t twice, but if you take this particular matrix and square it, it just gives you the 0 matrix. So in fact this is just going to be the 0 vector. So x square, well, in fact all higher powers of x, x cubed, x power 4 and so on, all of them act as 0. Okay. So in some sense all the information is only contained in these first two actions, that of alphas, that's constant polynomials, and the polynomial x. Okay, so that's my module. So what have I done for you? I have defined for you a module. So V in this case is a module over R. Okay, V is an R module. Why are these definitions? Okay, now I claim that in this context I can find an example of a submodule which does not admit a complement. Okay, so next task is to try and understand what submodules of V look like. And remember, this again is something that we have addressed before. If I need to find submodules, so this is all over the ring Kx. So the Kx submodules of V are the same as T invariant subspaces of V. Okay, so look back again on the lecture on submodules, where we talked about what submodules of modules over Kx look like. These are just T invariant subspaces. Okay, now what is a T invariant subspace in this particular example? That's all we are down to. So let's try and understand what are the T invariant subspaces. So suppose, so let me work on the right hand side. So let me try and look at this. So let M subset of K2 be a T invariant subspace. Maybe I shouldn't call it M, let's use some vector space notation. Let me call it W maybe. Let W subset of K2 be a T invariant subspace of K2. Okay, so what does that mean? So let me pick an element in W. So suppose I take the vector AB belonging to W. Now saying that W is T invariant means that when I act T on AB, the answer is again in W. Okay, now what does this mean? In this case, recall T does this special thing, it just sends AB to B comma 0. So what I conclude is that B comma 0 must be in W. Okay. Now if B is not 0, then this in fact tells me that I can divide by B, I can conclude that the vector 1 comma 0 is in W. Okay. So that seems to be some conclusion we can draw, that if suppose my invariant subspace has a vector AB in which this element B is not 0, then I can conclude that the vector 1 0 itself belongs to W. Okay. So what does this mean? Let's just take well, this sort of already tells us, gives us a candidate for a subspace. So let's look at the following candidate. So let's define a subspace. So let me call it maybe P. It's just a span of 1 0. Okay, in other words, it's all vectors of the form A comma 0, A ranges over K. Okay, so I claim that P is in fact P is an invariant subspace. So I claim that P is a T invariant subspace of K2. Okay, why is that? Well, because proof, if I just take any element A0 in P, in fact you see that what you get is just 0 0. Okay, because B is 0 in this case. So T of A0 is just 0 0. So of course that belongs to the subspace P. Okay, so this is T invariant for very obvious reasons, that it maps every element there to 0. Okay, so this is sort of trivial, but I claim more in fact that this is the only T invariant subspace of K2 other than the two trivial possibilities, which is 0 and the whole. Okay, so claim, the stronger claim, in fact the 0 subspace, the sort of one dimensional subspace P and the two dimensional subspace K2 are the only T invariant subspaces of K2. Okay. So, I claim that there are only these three T invariant subspaces. So, let us prove that. So, we have just shown that P is T invariant, these other two guys are of course T invariant. I claim there cannot be any others. Okay. Why not? Well, that is what we just tried to show here. Suppose W is a T invariant subspace of K2. Okay. So, let us pick such a guy. What do we conclude? If suppose I have a vector in W in which B is not 0, okay, then I conclude that 1 0 belongs to W. Okay. So, recall that's what this argument showed. So, let us now use that in this proof. So, I claim that these are the only T invariant subspaces. So, maybe let us argue by contradiction. If not, there exists a T invariant subspace W which is not one of these three. W which is not equal to 0, which is not equal to this space P, which is not equal to K2, right. Now, what does that mean? Okay, so what does that mean? In particular, it says that W is not 0 dimensional, W is not 2 dimensional. So, this tells you that W is not a 0 dimensional space, W is not the whole thing. So, W can only be some one dimensional space, right. So, that is what we have concluded so far. It is a one dimensional subspace, but further it is not equal to this particular special one dimensional subspace P. It is some other one dimensional space. Okay. So, W is one dimensional. So, all this is now thought of as vector spaces over K. So, we know for sure it is one dimensional and it is not this particular one dimensional guy P. Now, what is P? If you remember, P is just everything in the form A comma 0. Okay, and W is not this one dimensional space, which means that I can surely find a vector AB in W such that B is not 0, right. Why can I do that? Because W is not equal to P, right. If it is not P, then at least one vector in W must have a component, the second component here, which is not 0. Okay. So, there is a vector in W for which its second component B is not 0, but now we just use the argument that we used right here, the previous page, which said that if B is not 0, then I conclude that 1 comma 0 is in W. Okay. So, let us conclude that this means that 1 comma 0 is in W, belongs to W. Okay, but observe, what does that mean? 1 comma 0 is exactly the span of 1 comma 0 is exactly P, right. P is the span of 1 comma 0. Okay, so if 1 comma 0 is in W, then the span of 1 comma 0 is a subset of W, right. So, I conclude that P must in fact be a subspace of W, but that is not quite possible because this guy is also one dimensional and this guy is also one dimensional. Okay. So, both are one dimensional and I conclude one of them is a subspace of the other, then that the only possibility is that they are equal. Okay, but recall that is a contradiction because we started out under the assumption that P and W are not equal to each other. Okay. So, look back again on this proof. The one basic observation is this thing that we just made, that if you can find a vector in W whose second component is not 0, you can conclude that 1 comma 0 itself is in W. Okay. Now, what does that get us? Let us go back to this claim here. So, this claim tells us something very interesting. It says that there are only 3 subspaces which are T invariant. Okay. And recall, T invariant subspaces are the same as Kx submodules. Now, if these are the only 3 T invariant subspaces, then let me do the following. Let me take my submodule M1 to be P itself here. So now let's do the following. Let's take, so consider M1 to be P. So this is definitely a Kx submodule of K2. Okay, because it's T invariant, but observe this does not have a complementary subspace. Okay, why not? Well, because there aren't any subspaces possible. What are the only possible invariant guys? You can either take P, 0 or K2, right? And well, let's see, what do you need for a complementary subspace? At the very least, you need that the intersection of that with P should be 0, right? So I can't take P. P can't be the complement of itself because the intersection is not 0. K2 can't be the complement of P. The only possibility is 0 maybe because the intersection is 0, but P intersection 0 is 0, but P plus 0 is not the whole thing. Okay, so P plus 0 would just give me P itself. So observe that none of these three candidates can serve as a complementary subspace to M1. So observe that there does not exist a complementary subspace or a complementary submodule. Why? Because the only candidates, so there are only three candidates, P and the whole, none of them satisfy the requirement to be M1 directs M2. Okay, so complementary submodules don't always exist. You know, vector spaces are somewhat special in this regard. Okay, so there are many other instances where they do exist as well, but this is just to reinforce that what we are familiar with in the vector space context, one should be a little careful with trying to use those same sorts of reasoning in the case of general rings. Okay.